I'll keep this up and everybody sees it.
Yep.
Yeah.
Yeah.
So the occasion for this seminar has been given probably by Inigo, I would say.
Yeah.
You mentioned this direct preference optimization to me the first time, and I had the opportunity to have a big read about it, but certainly not enough to answer all sort of questions you may have about this type of particular approach, no? So the paper that presented this was the DPO paper of these guys. Not amongst them, there's Chris Manning. The paper is from 2023, was accepted and published in New Rips, which I think is towards the end of the year, but the archive version was already there since May. The paper is super interesting in my readings, but so is the supplemental. So in case you download it, be aware there's a supplemental. It's very, full of useful information. Who's Victoria? And when I prepared the draft of this presentation, and I started a couple of weeks ago, I checked the number of citations in Google, and we're already 3,000. So 3,000 in 2 years, roughly, actually less than 2 years. It's one of those super-cited papers that is making a massive impact in the field. So the two key bits of information about this particular technique, the PO, is that, yes, it is inspired by reinforcement learning, in particular from reinforcement learning from human feedback, what is known as RLFH, is an acronym, super popular in the LLM space, but is not, matter of fact, a reinforcement learning approach. Is a differentiable training objective, like the negative log likelihood. There's no sampling, no policy gradient, nothing. Is inspired, strongly inspired by that, as we're going to see. But matter of fact is a differentiable training objective. The second key statement is that unlike all the data sets that we have used to train all sort of tasks, using reference answers from the model annotated by humans, standard annotated training sets, the whole assumption is that what you have available is not the ground truth for a given input, but just two responses from the model and a relative ranking between them. Like, I like this response better than that, which is what is called a preference. Two responses for a given input.
One question. Could it be considered, like in the review I was doing for PPO, there was I remember the concept of offline and online reinforcement learning.
Yeah.
Can this one also be considered offline?
It's a totally offline.
Offline
Standard DPO, it falls into the category of offline.
Yeah.
I say with a lot of confidence. I actually learned it this morning at the Starbucks when I was reading the survey paper, so I don't. But it's offline because the rewards and the preferences are all, particularly the preference data sets, is given statically before training commences.
Yeah.
Whereas alternatives online generates preferences as the model goes.
Sorry, Massimo. The preferences, is it always limited to 2, or can you have many more with relative ranks between 2?
Excellent question. I don't know. I'm sure there's been, I'll show you how many variations around the themes have been proposed. It's staggering.
Yeah.
So I'm sure some of those might have used 3 preferences.
Yeah.
I've seen other alternatives, DPO again, in a survey paper that I'm going to mention, that use the 2 preferences and a ground truth together in the training objectives. So
the DeepSeek one also was grouped.
DeepSeek is the GRPO or GPRO, I don't remember which. So yes, there's a huge number of variations, despite the fact this was proposed only 2 years ago, has been like booming. Yeah. So before we explain how this direct preference optimization DPO works, we look at quick recap of reinforcement learning from human feedback. There is fundamentally 3 stages. The first stage is to carry out some kind of supervised fine-tuning, often abbreviated as SFT, acronymized SFT. The SFT model is the model that you obtain from the first supervised fine-tuning convention. I guess that is needed for a number of reasons. You want to have a model that performs decently before you start rating the preferences. So, or trying to improve. So fundamentally, this stage seems to be always there. A warm up with a supervised fine-tuning data set wherever it is available. Second stage is the famous reward modeling, where you build an explicit model to be able to reward your large language models. This reward modeling uses the current model, the SFT model, to generate two responses for a given sample, like provide X in input, two samples in output, other criteria, I don't know, maybe different prompts. So somehow you generate two responses for a given sample, and then you ask a human annotator to choose which of the two is better relative, and you label that YW, the winning or winner of the two responses, and the other, of course, by contrast, YL, loser, losing of the two responses. So you got these two preferences for every input. Your goal is to create a reward model that receives in input an X in whatever prediction Y and is able to assign Y a score. And therefore is a regressor, is something that outputs a number, not a class or a sentence. And this regressor is built using the same model, the SFT model, the supervised fine-tuned model that you have built, and you add one minimal layer that converts the final layer into numbers, like a final linear layer that outputs a number instead of a probability set. So a minimal addition over the model, and that will to become now about to train it the reward model. So that's why the paper was originally called Your Large Language Model is Secretly a Reward Model, because with the same model that is going to later solve the task, you also create the reward model itself. Fundamentally, it's the same. So how do you train this reward model? So you build the model using the SFT model with an extra layer, and now you have to train it to become a trained reward model. And you use this Bradley-Terry assumption, which pretty much is just a binary classifier. So you build a probability, which is exactly the probability of a standard binomial linear regression classifier, nothing regression classifier, nothing different. The probability you're trying to assign with that weird symbol, the greater than modified, means that Y1 is the better than Y2. So the probability that Y1 be better than Y2, and the probability that Y2 be better than Y1 add up to 1 by design. You got only two options. And the probability model is the standard probability model of a logistic regressor, X at the logit of the winning class, divided for normalization, X of the logit of the winning class plus X to the logit of the losing class. Super standard binary classifier. So how do you train it? With negative log likelihood, as usual. So you know in your set which one is the winner, which one is the loser. You simply train the model so that these two probabilities, that the winner be better than the loser, increases. Of course, at the expense of the probability of the loser being better than the winner, because the probability adds up to 1. So if you manage to increase these, the other, by contrast, goes down. If you develop that, so it could be not immediate effect. If you sigma is the standard 1 divided 1 plus e at the power of minus argument. So if you replace sigma explicitly and you use the two logits for the winner and the loser, you come up with exactly the probability above. So it's just a compact notation, but it's exactly the log of the prob that you see above for the winning label being better than the losing labels. The paper says that another thing, so this gives you the reward. Fundamentally, this trains R, which is the logit of this probability distribution trained with negative log likelihood, is your reward model. That given any X, any Y is able to assign Y a score given X. They say that they take the training set, they compute all these rewards, and then they subtract the mean, because for some reasons, zero-centered reward seems to be practically better than the otherwise. That's it. So you built your reward model, R of X and Y, and now you have to use it to improve the original large language model that solves the task that you are trying to, no. So you start with again, obviously with the model that you have supervised, fine-tuned. You have your reward model, and then you apply the standard policy gradient or any kind of form of policy gradient. You have your reward model, you generate samples, you give them, and then use that to now as the training objective. So the training objective in reality is a little bit different because in addition to the term to the left, which is the standard maximization of the reward, which is equivalent to minimizing the loss, the samples, just to give a little bit of reading of that formula, the samples y is sampled from pi of y given x, which is a very, is called the policy. Matter of fact, is just a large language model. Is the probability a large language model assigns to y given x. So given input, what probability? So super standard notation. Theta are the parameters of that large language model that we're trying to optimize. So the first part is just fundamentally the standard policy gradient objective, but they also add classic anchor term where they try to prevent the model from going too far away, to stray too much from the initial supervised fine-tuned model. So that's a classic Kullback-Leibler divergence between the models that you're training, the one indexed by theta, and the other one that is indexed by SFT or REFT, which is the model you have supervised fine-tuned in the beginning. So a balance between these two terms, the main objective and the regularizer. Beta establishes how much you want the regularizer term to weigh in the total.
So, but in here we are sampling references then from the model.
We haven't done, and we finished. The preferences have been sampled before.
Yeah.
And at the moment we're sampling responses. So the three stages are, the first is the supervised fine-tuning of your actual model. From that model, you generate some preferences, you annotate, and you create the reward model, which is that R function, which is fixed at this point, parameterized in phi, which is the parameters of the reward model. Yeah. And that is able to score any response given any x.
So the preferences are only used.
Preferences have been used before. Now there's no more preferences around. Just predictions by the model. The prediction gets scored. Based on the score, they influence the update of the parameters more or less. And the anchor term that tries to prevent the new model to stray too much away from the original. So that's the super standard, apparently as well, reinforcement learning from human feedback approach. The human feedback is collected in the previous stage, used to train the reward model. Once the reward model is ready, fixed is used to improve the tuning of your target model. DPO instead works differently. I notice now after a long time that this thing is visible on the screen, and this I'll move it away. DPO has this smart idea to pretty much target exactly the same training objective, but without building at all an explicit reward model. So that stage where we patiently build a reward model that is used to the improver is completely skipped, is completely implicit in the equivalence between the two models. The manipulation that ensures that this is the case is super elegant. That's why I like this paper a lot. It's not just try, see how it works. There's a beautiful, and I don't know if that manipulation is the author's work or exists from before, because they also acknowledge that all these models, the Bradley Terry and others it's been there for a long time. So, but fundamentally, this is the point. There is a proof that the optimal form of the reward function, that xy that rewards y given x, is in that shape you see for the objective that we just introduced. The regularized training objective, the optimal form that R should have to maximize it has to be beta, the regularization parameters, log, the probability of the model parameterized by the optimal reward, divided the probability of the reference model, plus beta, the log of the famous partition function. The partition function is famous if you work with logistic regression, is the denominator. In this case, it's horrible to compute, apparently, because there are so many cases, and so it's not normally feasible to create a reward that explicitly needs to compute that Z term in this equation. But where is the smart reasoning? Smart reasoning is that if you go back to the reward model, which was this one, no, where you have the log of sigma of those two, the reward of the winner, the reward of the loser, you replace the expression for both rewards with the one we've just seen. Because there's a difference, the partition function goes away. Because you got plus beta log z minus beta log z, so you don't have to worry about computing it at all. So you create this, replacing the optimal, the proven optimal shape for that particular function, and you obtain the training objective of DPO. This is DPO. DPO is this formula, is a training objective that contains two log likelihoods, two log probabilities, log pi theta, sorry. The pi theta is our model. Theta has parameters that we're trying to optimize. Appears 2 times. At the denominator, there is a constant. So it is a log probability, but that probability is frozen because the model, the ref model is frozen. So pretty much you have to compute the log likelihood of the winning response and the log likelihood of the losing response. And you optimize your backprop through those two things. All the rest are just terms to ensure that the objective obtains exactly the same target of optimizing that regularized training objective with reinforcement learning, but you don't have to do any sampling, you don't have to do anything because it is equivalent without the need for sampling.
But that's why it's called direct preference optimization, if
Yeah.
you're using preferences.
You use preferences also in the other, but in the other, you have to
directly
build the reward model.
Yeah.
And here you skip the building of the reward model, you just go for the optimization of the target.
Yeah.
Which is what those pictures below try to state.
Yeah.
So that's it. Pretty much this is the key. It may be heavy to compute because you need for every YW and YL, you need to compute the response. Maybe you can do it once and for all for a given X because that's a frozen term. I don't know how practically to make the computation of these training objective more efficient, but it's actually quite simple in terms of what it looks like.
Yeah, but it's a likelihood, right? So you can
It's a likelihood.
parallel.
It's two likelihoods. So it's like normally you would have the likelihood of the ground truth, no?
Yeah.
Y ground truth, the best possible response.
Yeah.
Instead, now you have the likelihood of YW, the winner of the two preferences. You subtract like the likelihood of the the losing label. But fundamentally is of comparable complexity or to a standard negative log likelihood. That's it. So that's it for the theory. I just try to read not too much in detail the experimental evaluation that was presented in the paper itself. They used 3 tasks of natural language generation. One is called controlled sentiment generation. Another is summarization. Another is single-turn dialogue. All generative tasks, of course. So I just read carefully the first and I'll present briefly. So what is the task controlled sentiment generation? They take the classic IMDb dataset, they take the review, the positive reviews only, and they take the first few tokens between 2 and 8, use them as a prompt, and they expect the large language model to output, not exactly the rest, but to output consistent review with the prompt that would be of positive sentiment. So they expect completion, review completion from the prompt with the prescribed positive sentiment. So the advantage of this is also that you have some ground truth because you have the original review. It's obvious that people can complete the prompt in many acceptable ways, but at least you have one ground truth per input if you want to leverage it. So in this case, they don't use any manually annotated preferences. The 2 preferences, the winner and the loser, are generated automatically from a pre-trained sentiment classifier. So you generate 2 responses per input from the supervised fine-tuned model, and you ask this model to just score them in terms of sentiment. when you do that, people sometimes call it reinforcement learning from AI feedback. So a slight variations around the human feedback because there's no human involved at annotating the two preferences. Obviously, the one that scores better for the prescribed sentiment is labeled winner, the other is labeled loser. For the experiment back then, 2 years ago, they're still using GPT-2 large, so not a massive model, 774 billion parameters. And the main approaches they compare, you see them here. Obviously, their own approach, the DPO, compared against a standard implementation of PPO, so reinforcement learning from human feedback, in this case from AI feedback with PPO as the policy gradient algorithm. A version from PPO that instead uses the ground truth, the undisclosed review. So what could be better in a way? So it's got this advantage of using Oracle data. And then you have the a simple fine-tuned model with the preferred of the two, just fine-tuned with the winners. Could be another strategy. And then there's one of the many other alternative methods. By the way, you remember the expression unlikelihood, that at some point you were looking for that, no? And it's just a model that uses the two labels in a more conventional way, put them in the objective, increase the probability of one, decreases the probability of the other. So this is the main results plot, and I find this staggering. In fact, I called it a massive result because how do you read this? First, what is plotted? What they're plotting is what reward. So when you go back to this training objective here, the reward term is to the left and the divergence with the original models to the right. What you want here is to maximize R and keep the divergence as small as possible, but any actual model will be a trade-off between the two. So looking at the trade-offs you're able to achieve, the yellow dots are the DPO. The yellow dots beat all other methods by far for any possible combinations of divergence and reward. So wherever you want to see that, no, so what you want is a high reward and low. You want to be on the left side of that plot to have as little divergence with the original model as possible, but still get a good reward. See how quickly DPO rises, gets to very good levels of reward with minimal divergence from the supervised fine-tuned model. And if you still accept more divergence, it's still on top of all the other models by far. In every single operating point of that trade-off is amazing. It's not just like, compromise here and there, certain regions, is across the board has surpassed all those models that I briefly explained in the previous. So PPO GT is using the ground truth, their own implementation, GT-TRL, TRL is a library. So they tried, seemingly honestly, to make the competitive models work well, but still these DPO were much, much better. And similar results, of course, for the other two tasks that were part of the evaluation.
But the objective function you showed for DPO, did you just show the left part? Because I didn't see they were controlling for KL divergence.
So the story goes that the optimal reward for this
is
this. So it's provenly optimal to obtain the maximization of this trade-off. So you don't explicitly improve one or the other, you improve the sum, and beta plays a big role because beta is your balancing coefficient that balances.
So it's already there, right?
The two terms is already there.
Yeah.
So by choosing this form in this training objective, you ensure you optimize the model with both the main objective and the regularizer for the chosen beta, which is obviously probably the key hyperparameter. That's it. So that's pretty much the presentation. But in terms of follow-up work, I was trying to build a bit who's cited these and who has cited, what is the latest shout in this particular line of work. And I came across this amazing paper published less than a month ago. Again, Touch and Tao. Amazing. I mean, the fact that this guy has been able to author an incredible number of highly cited papers, including this one. after being with Sydney Uni for many years as an Australian Laureate Fellow, just for reference, he moved back to Singapore. So he's now in NTU in Singapore. And the first author of this paper is one of his PhD students. But there's a long list of authors, of course, all from Alibaba and other Chinese companies or teams. So it may not be possible to make it bigger, but the message I want to say here, if you're thinking about improving DPO, don't. Or if you think you can improve DPO, be aware that between you and that, there's hundreds of variants that have been published in the last 2 years, including, I tried to, DPO itself, I think, is that little red circle there. Up there, there's I need to take my glasses off, GRPO, which is the variant used by DeepSeek just recently to fine-tune DeepSeek. So pretty much every training objective that has been is here. The authors of this paper have done, I believe, an excellent job at trying to offer not just comprehensiveness, but some dimensions under which to try to compare and taxonomize these models. So the 4 outer here are the 4 categories or dimensions. They look at these various techniques in terms, for instance, of the regularizer. The regularizer doesn't need to be just that. You can use whatever other term to try to steer the model to behave in a certain way or not. Or the model itself, the trade-off between exploration, optimization. So they try to make this as neat as possible, creating 4 major viewpoints from which to categorize these techniques. And that's what they come up with. Seems to be a pretty neat, at least, survey effort. Talking about, in particular, the regularizer, in addition to the divergence constraint, there's been extensive use of what's called safety constraints, which are constraints that people add to the training objective in order for that to avoid being harmful, maybe reduce hallucination, but in particular, the harmfulness, the risk of starting saying things which, there's a lot of work around the loss in ability to utter certain things because of the compromise. So the literature is huge. This paper, I haven't read it fully. I've just started to read it recently, but it's very interesting. The survey contains also a survey of key data sets and key benchmarks. And a big survey of comparative results of these. So the main techniques, they've also run them. So it's a comparative survey, it's an experimental survey where they use these base models, MISTOR 7B, ALAMA 3.8, ALAMA 8B, ALAMA 8B with instruction fine-tuning. So they used serious baselines. And in addition to that, they compared all these over benchmarks of note. So it's an incredibly rich survey paper.
Big work.
Absolutely big work, worth reading in case you intend to use it. I would say you need to read this paper first of all. In the survey paper, again, the authors point to the main applications for large language models, obviously, but not only, also for multimodal, so with images and text, but also apparently diffusion models like DALL-E, to generate images. These training objectives are also very effective. Preferences, I like this image better, given the prompt. Challenges that they list as open, the efficiency. The efficiency is a big challenge, apparently. Efficiency in terms of how many preferences, what quality of preferences you actually need in order to be able to improve performance. Multimodalities, preferences over maybe captions and images and videos and segmentation. So dynamic preferences, people changing their tastes. People who watch movies over time, liking, changing predictions, and interpretability, because by itself, the approach is completely black box. I came across, because they mentioned it, this transformer reinforcement learning library that, again, I didn't really know, but it's got everything that you know. It's got DPO, it's got PPO, it's got heaps of those techniques mentioned there. If you want to please note that the preference data set should be sampled from your own model. Yeah. Thank you. Thank you very much, Bang. I saw your notes in the chat. Yeah, that's what they mentioned, that the preferences should come from your model. I think that the only option is whether you want to rate them manually or you want to rate them with some auxiliary pre-trained model outside, just to save you the effort.
People use the public dataset too, but first they do an
Sorry, I
FFT.
kept my volume so low. I don't know why, to be honest, because it's on 65%, but no one in the room probably heard your question or comment. Could you say it again?
Let me check. Can you hear me? Hello?
Not particularly. I'm sorry. I don't know why, because maybe
It's plugged in.
Yeah.
because it's plugged in. Sorry, I can hear you. Or if you want to type it in the chat, I'll amplify for everyone.
Okay.
Maybe you can just type.
Yeah, I was suggesting that. Hi, Victoria.
Yes. Second part, yeah.
Yeah. So thank you very much, Bang. Bang was pointing out that even if you are using a pre-trained model, it's still recommendable that you do the supervised fine-tuning in order to align as much as possible the model to the task before the preferences are used one against the other. So you could, for instance, supervise fine-tune it with the winners of the two preferences or something. Yeah.
Yeah.
Thank you very much. So back to this, just a brief mention to that, and also came across this wonderful course. This course was online and still is online, but the gentleman, Maxime Labon, has decided also to put it into a more conventional form of an engineer's handbook. And I browsed a little bit. He's so smart to distinguish between the role of an AI scientist, an AI engineer, the different stages at which certain skills may come into play. And I just found it because I was looking for an example of use of this TRL library. And I came across this Mistral 7 billion model fine-tuning with DPO. So in case you want to have a look at how they implement a DPO. And I guess it won't be the only one just yet. I bumped into this. And that's my last thing, I think. Yes, that's it.
Yeah, cool. Thank you. It was very good.
Actually, the implementation is with TRL, the one I have now with DPO.
Yeah.
And it was fine-tuned, so we are not far away, which is great.
Excellent.
And I work with his material. It's really good.
So we kind of spontaneously align because the work must be so good that pretty much you bump into it as soon as you start browsing
I've been following
this space.
for a while. Like he has plenty of material for like models. And it's well explained, that's nice part.
So we have 5 in this room and someone is online. If you have any questions, we do because for some reasons the audio doesn't work from online to the room, but we'll work it out if you have any questions. Otherwise, I can keep it to this. Peter is still in a bliss for passing his CA1. You are uncharacteristically quiet. That's good. Okay. All right. Nice. Thank you for coming along.
Thank you.
I believe the video, as I said, the recording as soon as
we can put the
finish.
slides in the repository too.
Yeah.
Yeah. If you send
Excellent.
it to me, I can.
Yeah, I'll do both.
Can you have
Okay.
this recording?
Yes, I was looking well because when it's smaller, the recording button disappears. Here it comes. All right.
Thank you.